Welcome back to an introduction to real analysis. We continue now in Chapter 5, Section 2, Properties of the Riemann integral. So first we're going to address additivity. Adding a bunch of things in two parts, and then adding those two parts together should be the same thing as adding all of those things all at once. In a finite number of terms with just real numbers, this is really just the associative and commutative properties of additivity. Now, the corresponding property for integrals is called the additive property of the integral. We're going to prove the additive property for lower and upper Darboux integrals, and then we'll try to put it together to Darboux integrals in general. Now, the fundamental obstruction to this is that if P1 is a partition of a set S1 and P2 is a partition of S2, then certainly P1 union P2 is a partition of S1 union S2, but not every partition of the union of S1 and S2 will automatically become a partition of S1 and a partition of S2 together. So let's look at this example. Consider the interval 0, 1 and the interval 1, 2. Now, let's let our first partition be the points 0, 0.3, and 1, and our second partition be 1, 1.1, 1.7, and 2. Then if we union them together, we get 0, 0.3, 1, 1.1, 1.7, 2, and that's definitely a partition of the interval from 0 to 2. However, 0, 0.6, 1.2, 2 is a partition of the interval from 0 to 2, but there's no way to break this apart into two sets, one of which is a partition of 0, 1, and one of which is a partition of 1, 2, because the partition we made does not contain that endpoint 1. For the union 0 to 2, you don't necessarily have to include the point 1, but if you want to make a partition of the interval from 0 to 1, you definitely do. So what we can do is we can refine any partition of 0, 2 by adding in the single point 1, and then we will be able to split it into two partitions, one of the interval from 0 to 1 and the other from the interval from 1 to 2. Now this refinement trick is something we're going to use several times to establish additivity of upper and lower Darboux integrals. So we proceed with this lemma. Suppose a is less than b is less than c, and f maps the interval from a to c to the reals, and is bounded. Then, both of the lower and upper Darboux integrals are additive. The lower integral from a to b plus the lower integral from b to c will recover the lower integral from a all the way to c. And similarly, the upper integral from a to b plus the upper integral from b to c will be the upper integral from a all the way to c. As always, we got to prove such things. Now, partitions of the interval from a to c which contain the point b are in fact a subset of all the partitions from a to c. So a supremum over the former cannot be larger than a supremum over the latter because it's a subset. Now, if we take any partition of a to c whose lower sum is extremely close to the lower integral, then, if we simply union that partition with the single point b, we make a refinement. And what happens to lower sums when you make a refinement? They can only get larger. So, the lower sum of this refinement is at least as large as the lower sum of p we started with. But we can start with this p to be a partition of the interval from a to c whose lower sum is arbitrarily close to this lower integral from a to c. So, we can take a supremum just over partitions of a to c which contain b. The partitions which contain b are a subset, so if we take a supremum over that, the supremum will be less than or equal to the supremum over all. However, any partition arbitrarily close to the lower sum, I may refine it and turn it into a partition which contains b. So a supremum over these partitions will be bigger than or equal to a supremum over these. Altogether, the supremum over partitions that contain b equals the supremum over partitions overall. So, since the supremum of lower sums of partitions which contain b equals the supremum of lower sums of partitions which may or may not, we can now take any partition of a to b and any partition of b to c and union them together to get a special partition of a to c which contains the specific endpoint b. Now, for this particular choice of partition, the union of these two, we get the lower sum of the overall partition is simply the sum of the two lower sums, the left part from a to b and the right part from b to c. So if I take a supremum over these, I will recover a supremum of these plus a supremum of those. So the supremum of lower sums for partitions which contain B is in fact equal to the supremum of lower sums of arbitrary partitions from A to B plus the supremum of lower sums of partitions from B to C. So what do we have altogether? The lower integral from A to C is the supremum of lower sums over arbitrary partitions from A to C, but we've established that's the supremum of lower sums where the partition is specifically required to contain the point B. However, we also found that that's the supremum of lower sums of any partition from A to B plus the supremum of lower sums of any partition from B to C, which is exactly the lower integral from A to B plus the lower integral from B to C, establishing the first claim of this lemma. The second is proved exactly analogously. We're leaving out those details. Let's now take a look at proposition 5.2.2. Suppose A is less than B is less than C, then the function f, whose domain is the entire interval from A to C, is Darboux integrable if and only if it is Darboux integrable both on the interval from A to B and the interval from B to C, in which case we have additivity of the integral. The integral from A to C is equal to the integral from A to B plus the integral from B to C. Okay, moving on to the proof. Now, in the previous lemma, we established that we had additivity for upper and lower Darboux integrals. So, if f is integrable on both the intervals from A to B and B to C, then what do we have? We have that the lower integral from A to B is equal to the integral from A to B, and the lower integral from B to C is equal to the integral from B to C. So the lower integral from A to C is equal to the sum of these two integrals, but also the sum of these two integrals will be equal to the sum of these two upper integrals because f is assumed to be Darboux integrable on both of these intervals. But in the lemma, we established that this sum is equal to this upper integral from A to C. Altogether, the lower integral from A to C is equal to the upper integral from A to C. Therefore, the value of the integral from A to C is whatever this common value is, which is exactly the sum of these two Darboux integrals on the subintervals A to B and B to C. That's essentially the straightforward direction of this proof. If the function is integrable on both of these smaller intervals, then I can glue together these integrals to make this one right here. Which means we have to prove the other direction. Suppose that f is Darboux integrable on the interval from A to C. In other words, the upper integral equals the lower integral. Then what does the previous lemma give us? That the sum of the lower integrals from A to B and B to C is equal to the lower integral from A to C, which is now assumed to be equal to the upper integral from A to C, which is the sum of these two upper integrals. So the sum of these two lower integrals equals the sum of these two upper integrals. We simply need to establish that this single lower integral equals this single upper integral, and this single lower integral equals this single upper integral. Now, the lower integral from A to B is less than or equal to the upper integral from A to B, and similarly for the interval from B to C. So the only way, if this is less than or equal to that, and this is less than or equal to that, the only way I can sum together these two things, which are individually less than or equal to these two, and achieve equality, is if this is equal to that and this is equal to that. If we had a strict inequality on either one, then when we added them together, we would maintain the strict inequality and we would have a less than here. Since we actually achieve equality, and this lower integral is less than or equal to this upper one, and this lower integral is less than or equal to this upper one, the only way we can end up with this equality is to have equality all around. So now we have established that f is Darboux integrable on the interval from A to B and on the interval from B to C. Therefore, we can assign this shared value to be the integral from A to B, and this shared value to be the integral from B to C. And now lemma 5.2.1 establishes that the lower and upper integrals, which we assume to be equal at the beginning of this direction of the proof, are equal to the sum of these two things, and these are both equal to each other. And we recover the claim of prop 5.2.2. Let's now take a look at corollary 5.2.3. Suppose f is Riemann, in other words Darboux, integrable on the interval from A to B, and C to D is a subset of that interval. then the restriction of f to that interval c to d is also Riemann or Darboux integrable. Now the proof is left as an exercise. You need merely look at the previous proposition and lemma and piece together a couple of steps. So let's talk about that. We remind you that we are conflating notation between Darboux and Riemann integrability. Equivalence of the two types of integrals was established in the exercises of the previous section. So while we're stating results with the notation Riemann integrability, because that's by far the more common notation, our proof techniques are all grounded in Darboux integration. So I just want to take this opportunity to stress you really should work through those trio of exercises, 5.1.7, 12, and 13, to understand why Darboux and Riemann integrability are exactly equivalent. The notation is all grounded in Riemann integrability. That's how people write it, and that's kind of how we keep talking. But our proof techniques are all about Darboux integrability because the proofs are honestly easier to put together there. So make sure you understand why the two notions are equivalent. Okay, let's move on to establish some basic properties of how to actually compute integrals. Proposition 5.2.4. Suppose f and g are both integrable on the interval from a to b and alpha is some constant. Then alpha times f is integrable, and the integral of alpha f is simply alpha times the integral of f. In other words, scalar constants factor in and out of integration. Also, f plus g is Riemann or Darboux integrable, and the value of the integral of f plus g is simply the integral of f plus the integral of g. In other words, you may distribute, so to speak, the integration across a sum of two functions. Going on to the proof. So first, let's assume alpha is not negative. If alpha equals 0, the proof is very easy to establish merely through definitions, but will also be covered by the following argument. We're just letting alpha be non-negative, so we don't have to flip inequalities when we multiply by it. Now, for any partition of the interval from a to b, and any little sub-piece of that partition, xi minus 1 to xi, as alpha is not negative, alpha times the supremum of f is simply the supremum of alpha times f. Therefore, the lower integral from a to b of alpha f is the supremum of lower sums of alpha times f, but that's just the supremum of alpha times the lower sum of f. That alpha factors out of the supremum, again, because it is not negative, and we end up with the lower integral of alpha f is alpha times the lower integral of f. So having established that the lower integral of alpha f is equal to alpha times the lower integral of f, we can similarly prove that the upper integral of alpha f is alpha times the upper integral of f. And since f was assumed to be integrable, the lower and upper integral of f from a to b is equal, so multiplying by the scalar alpha maintains equality. We now have that the upper and lower integrals of alpha times f are equal, and the result follows. Now, in the previous proof, we relied on being able to factor scalar multiplication out of certain suprema. If alpha is negative, the proof is very similar, but you have to be careful about what's a sup and what's an inf, what's a lower integral and what's an upper integral. It is left as exercise 5.2.1. The second claim about sums f plus g is also left as an exercise in 5.2.2. So we omit the proof, but you should be able to pause, take a moment, and establish it for yourselves. It is an exercise. Now, additivity is not a trivial result. For two functions f and g, on any particular interval of a particular partition, in general, you do not have that the supremum of f plus g is equal to the supremum of f plus the supremum of g. So the proof that the integral distributes, so to speak, across a sum of two functions is not quite as direct as you might first think. Upper and lower integrals, the equality might not hold. The upper integral of f plus g might not in fact be equal to the upper integral of f plus the upper integral of g. Now, if f and g are assumed to be integrable, you will be able to cover this result. But for an arbitrary function f and g, you cannot. So whatever your proof in that exercise is, integrability of f and g is key to proving that the upper integral of f plus g is equal to the upper integral of f plus the upper integral of g, and similar for lower integrals. Okay, now the proof of the following is exercise 5.2.16, and refer back to exercise 1.3.7 for some steps. Proposition 5.2.5, let f and g both be bounded functions. Then we get some inequalities with upper and lower integrals. The lower integral of f plus g is always bigger than or equal to the lower integral of f plus the lower integral of g, and the upper integral of f plus g is less than or equal to the upper integral of f plus the upper integral of g. Again, the proof of this proposition is left as an exercise. Now let's establish a result about monotonicity. Remember, for just real number inequalities, we have this basic result. If a is less than or equal to x, and also b is less than or equal to y, then a plus b is less than or equal to x plus y. Now maybe a similar result can hold for integrals which are related to sums. So here is proposition 5.2.6. Suppose f and g both have domain, the interval from a to b, they're bounded functions, and f of x is less than or equal to g of x for all points x in the interval from a to b. Then the upper integral of f is less than or equal to the upper integral of g, the lower integral of f is less than or equal to the lower integral of g, and if f and g are both integrable, then we maintain this inequality for their integrals. As always, we have to look at the proof. Now for any interval, which is a subset of the domain from a to b, point-wise, f of x is less than or equal to g of x, so the same inequality holds for both the supremum and the infimum over any particular interval. So for any partition, those inequalities holds on every piece of the partition. So I can then get those inequalities for the lower and upper sums. Now I can take the sup of the lower sums and the inf of the upper sums to immediately get the first two claims of Prop 5.2.6. And now, if I assume f and g are both integrable, because this upper sum equals this lower sum and this upper sum of f equals this lower sum of f, I get the inequality we wanted. So Prop 5.2.6 comes together pretty quick. So let's think back and remember Prop 5.1.13. If you have a bounded function on the interval from a to b, f is Darboux integrable if and only if, for any positive epsilon, there is a partition, P, where the upper and lower sums differ by less than epsilon. So linearity and monotonicity of the integral are basic steps that help us compute what the actual value of certain integrals is, but they rely on knowing that certain functions can in fact be integrated. So we're now going to work to understand which functions are integrable, and that proposition is going to be our main tool. We can establish a function is integrable if we can show that there are partitions whose upper and lower sums differ by arbitrarily small amounts. So let's look at lemma 5.2.7. Suppose f is a function which is continuous on the interval from a to b, including the endpoints. Then f is integrable on that interval. How would we prove this? So we're going to rely on an old result that honestly we have not cited once since we proved it. If a function is continuous on an interval including its endpoints, then it is uniformly continuous on said interval. Also, here is our condition for integrability. Can we find a partition whose upper and lower sums differ by an arbitrarily small amount? Now, since f is continuous on an interval including its endpoints, it has a maximum and a minimum. In other words, it's bounded. Now let epsilon be arbitrary and positive. By uniform continuity, there must be a fixed positive delta so that for any x and y, if x and y in the domain are less than delta far apart, then f of x and f of y are less than epsilon over b minus a far apart. So from uniform continuity, we have a fixed delta so that if I take any partition, every piece of which is less than delta in length, f is continuous on every piece of the partition, and therefore on each of these intervals does not just have a sup and an inf, but a genuine max and a min. So they are achieved at two specific points in the domain. But because these 2 points in the domain are in one of these intervals, they are less than delta xi far apart, the length of the interval that they belong to. But every delta xi was assumed to be less than little delta in length. Therefore, so for each piece of this partition, the max minus the min is less than epsilon over b minus a. Meaning when we add up such sums across all pieces of the partition. In other words, we recover the upper and lower sums. Here, the upper sum is simply the sum of capital Mi delta xi, and here we have the lower sum is the sum of little mi delta xi. These are summed over the same range of indices with a shared factor of delta xi, so we end up with this big Mi minus little mi that we can factor out of every term of the sum. Now, each of these is less than a fixed constant epsilon over b minus a, which we may factor out of the sum altogether, leaving behind just a sum of the delta xi's, which, as we have mentioned a few times, is exactly b minus a. That cancels this denominator. We recover epsilon. So we found a particular partition for which the upper and lower sums differ by less than epsilon, establishing integrability. So continuous functions on intervals, including their endpoints, are integrable. This is a major step forward in deciding which functions can or cannot be integrated. Next, we can establish integrability for another class of functions. If f has domain, the interval from a to b is monotone, then that function is Riemann and therefore also Darboux integrable on this interval. Now the proof is omitted. It is left as exercise 5.2.14. I would merely advise you consider uniform partitions of the interval. Remember, uniform partitions are those where every piece of the partition has the same width. So, continuous functions are integrable, monotone functions are integrable. Also, back in Prop 5.2.2, we established that if a function is integrable on an interval from a to b and from b to c, then it is integrable on the interval from a to c. Therefore, any function which is piecewise continuous or piecewise monotone are integrable. We will prove this in just a moment. Now that covers a whole lot of functions, piecewise, either continuous or monotone. But we still don't have a great idea how to compute the actual value of the interval. So here's lemma 5.2.8. It's a little technical in its phrasing, but let's take a look. If f is a bounded function from a to b, now we have a sequence an and a sequence bn with the following restrictions. An to bn is always a subinterval of a to b, but the an's, the left endpoints here, are converging to a, not necessarily decreasing to it, just converging to it. And bn's are converging to b, again, not necessarily increasing, but converging to it and always less than. Now, if f can be integrated on each of these intervals, then f can be integrated overall from a to b, and the value of the integral from a to b is the limit of the value of the integrals from an to bn. Okay, so let's prove that. Let capital M be a real number, which is an upper bound on the absolute value of f of x, overall from a to b. Now, since the interval from an to bn is a subinterval of the integral from a to b, we have the following inequality. B minus a, the length of that interval, is bigger than bn minus an. So, with that in mind, we get the following. Assuming f can be integrated from an to bn, that is an assumption in this lemma, the value of the integral is certainly in between the upper bound on the absolute value and the lower bound on minus 1 times the absolute value. In other words, capital M and minus m are upper and lower bounds on the function overall times the length of that interval. Now, bn minus an is less than b minus a, and bn minus an is less than b minus a, but because we have a negative multiplied here, that reverses. So, the integral from an to bn of f is bounded. There is a fixed upper and lower bound on the value of this integral. So indexing that by n, we have a bounded sequence. We can apply the Bolzano-Weierstrass theorem. We take a subsequence so that on this subsequence of ank to bnk, the values of this integral are converging to some fixed constant L. So we now have a subsequence, ank and bnk, along which the value of the integral is converging to L. Now by lemma 5.2.1, the upper and lower integrals are additive. So since f is integrable on all of these little intervals from an to bn, we get the following. The lower integral from a to b can be represented as the lower integral from a to ank plus the lower integral ank to bnk, but because f was integrable here, that lower integral is just an integral, and then a lower integral on this missing piece, bnk to b. Now we use the fact that the absolute value of f is bounded above by capital M. So the value of the lower integral is bigger than or equal to the value of the lower integral here, negative capital M times that length. This was just the value of an integral. We are leaving that the same. And here we again say the value of this lower integral is bigger than or equal to negative M times that length. Now we know that the limit along this subsequence of the integral from ank to bnk is L, and we've established this inequality right here. As k goes to infinity, ank is converging to a, so this is converging to 0, but similarly bnk is converging to b. This is converging to 0. This is converging to L. So the lower integral from a to b is bigger than or equal to whatever that limit L is. Okay, we have now established the lower integral from a to b is bigger than or equal to L. The same argument holds with upper integrals. You can go back and check. You'll end up with the upper integral from a to b is less than or equal to L. So now we have the lower integral bigger than or equal to L, bigger than or equal to upper integral, but the lower integral is always less than or equal to the upper integral. So these two things are in fact equal, and therefore they are equal to L, which was the limit of the integral from ank to bnk of f. Okay, so now we know that f is integrable on a to b. That was a key thing we had to establish. We also know the value of the integral is the limit of the integral from ank to bnk, but that's on a subsequence, ank to bnk. We want to claim that we can just take a limit overall. Now for any sequence for which this sequence of integrals converges, we have to be converging to the same thing, which is a fixed value. We just assumed let ank and bnk be a sequence along which this sequence of integral values converges to something. We were then able to show that the integral from a to b of f was that value, but the integral from a to b of f doesn't change if I change this subsequence. In other words, any subsequence we pick for which this sequence of values converges, it has to be converging to this fixed number, the integral from a to b of f. So every convergent subsequence of the sequence of integrals converges to the same thing. Way back when, Prop 2.3.7, if a sequence is bounded, it's convergent if and only if every convergent subsequence converges to the same thing. And we just showed this bounded sequence has the property that every convergent subsequence must be converging to the same thing. Therefore, this sequence overall is converging, and it's converging to that thing. Finishing the proof of lemma 5.2.8. So on to theorem 5.2.9. Let f be a function with domain the interval from a to b. Suppose it's continuous at every point except the set S, but S is a finite set. So the function f is continuous except at finitely many points. Then the function can be integrated. Can we prove it? Okay, just use the set S to partition a to b into finitely many intervals. And the condition is that f is now continuous on the open interval from ai to bi because we used the discontinuities to make our partition. Now on each such interval, we can make ci and di sub n be points converging to ai and bi. Now, the limit of cin is equal to ai, the limit of din is equal to bi, and f is continuous on the interval from cin to din, including those points, because the AIs and BIs were exactly the points from our partition, which was exactly the set of discontinuities. So by letting these C's and D's be interior to these points, we have continuity on the interval, including the endpoint. Therefore, the function is Riemann integrable on that little interval. So by what we just proved, since the function is integrable from CIN to DIN, and CIN is converging to AI and DIN is converging to BI, we get that f is in fact Riemann integrable on every piece from AI to BI. Now we have finitely many pieces, so we use the additivity of the integral to glue these pieces up and establish that f is integrable on that finite union, which was just the interval from a to b. It's very crucial here, by the way, that we have finitely many pieces. Okay, we established that you can take a function that is Riemann integrable on two intervals and glue them together. Inductively, you can now do that for any finite number of pieces. If you had infinitely many pieces, this would get much trickier, and it's worth stating, perhaps false. So let's discuss a little bit more on integrable functions. Sometimes it's very convenient or even necessary to change certain values of a function before integrating. Now, what we're about to establish, our next result, says that if you do this finitely many times, you take the function you started with and you change its value, but only at finitely many points, then the integral does not change. And the argument is again inductive. It's important we're only doing this at finitely many points. The proof is left as exercise 5.2.3. Just bear in mind the same technique as in the proof of theorem 5.2.9 will work, and you're going to want to cite prop 5.2.2 somewhere along the way. So here is that proposition. We're not going to prove it. Let f be Riemann integrable from a to b. Let g be a function from a to b that is equal to f except at a finite set of points, which we call s. Then g is also Riemann integrable, and the value of the two integrals is the same. So if you change finitely many points at a function, it does not affect integrability and it does not affect the value of the integral. Again, proof is left as an exercise. Now let's review everything we've just talked about. We established a few important properties of Darboux integrals. First, integrability passes to subsets and unions. Integrals are additive on disjoint sets, disjoint except perhaps at the endpoint. Integration also passes to sums of integrable functions, and integrability of a function is not changed if we change the value at finitely many points. Furthermore, the value of the integral is not changed. We also showed that if a function is continuous, or if a function is monotone on an interval from a to b, including the endpoints, then that function is integrable. We use that to derive that functions which are piecewise monotone or piecewise continuous are also integrable. But what's missing is a way to actually compute the value of the integral, and that is the main topic of the next section.